Okay, today we're going to carry on with another transform section problem. In this case, we're going to be looking at a reinforced concrete beam with reinforcing steel in the bottom of the beam, or in the tensile component, if we assume a positive moment. And this is really important because we do this all the time in concrete. Concrete is a very traditional composite construction using internal reinforcing steel and concrete. They behave differently. And so this is going to empower us to do it. Now, concrete is a little bit more interesting than the last example we did because, of course, it behaves very differently in tension than it does in compression, or specifically, it has very weak capacity and tension. And because of that, what we're going to do is we're going to assume that the contribution that the concrete makes when it's in tension is negligible, and we will discount it, other than, of course, it maintains the integrity of the beam and holds the reinforcing steel in the location where it is placed. So with that, why don't we jump into it and we'll see how it comes about. We've laid out the problem. We have a moment of 60 kilonewton meters. Dimensions of the beams are shown, and we've also given the moduli of the steel and the concrete is 200,000 megapascals and 25,000 megapascals. So we're going to start. We're going to transform the section. To do that, I need to know the area of the steel. I'm going to turn the steel into an equivalent area of material with the same stiffness as the concrete. So let's do that. So I'll just choose a pen. Area of the steel equals, so 1 bar would be pi r squared. We have 2 bars, so it's 2 times pi r squared. That's equal to 2 times pi times our radius, which is, what do we have here, 25 millimeter bars, so 12.5 millimeters is the radius. That is squared, and all of that should come out to 981.7 millimeters squared. Now we need the transformation factor for the transformation. So that's n, and of course n is always a ratio of the moduli, and so it is as a numerator the modulus of the material being replaced divided by the material you're replacing it with. So we have E of steel over our E of concrete. So that's our 200,000 megapascals, all divided by 25,000 megapascals. And when I run that through the calculator, I get a factor of about 8.0. So now the equivalent amount of area is just n times the area of the steel. And so we'll call that A prime as our transformation area. And that is equal to n times area of the steel. And so we have 8.0 times 981.7 millimeters squared. And we get a value of 7,853.6 millimeters squared. So that's the area we're going to use in our transformed section. So I'm going to just pop out, so the example where I've taken this from, they've got a really good representation or graphic that shows the transform section. So I'm just going to pop out, grab it, put it in here, and then we can carry on with the solution. Okay, there we go. I've popped in the diagram. We can see the transformed area. We've also removed all of the concrete material below the neutral axis because that's going to be in tension, with the exception of the transformed area replacing the steel, so behaving as the steel. So now what we need to know is we need to know the location of the neutral axis. And so we see here they've introduced H prime. That's going to represent the distance down from the top for the location of the neutral axis. So the easiest way for us to do that is we're going to figure out or the distance to the centroid, if you will, from a reference point. In this case, we're going to choose the reference point as the neutral axis itself. We know that that passes through the centroid. So ultimately, the distance has to be equal to 0. So in this case, we have y at I, a at I, and that must be equal to 0. And so we have two areas to consider. We have the concrete at the top, so that is going to be 300 millimeters times its height, which is h prime, and the distance to its centroid is h prime over 2. And so to that, then we have below the neutral axis, so in a negative distance, we have our area, which was 7,853.6 millimeters squared. And the distance there, if you look at it, is going to be the 400 millimeters, which is the depth, less the distance h prime. So 400 millimeters minus h prime. And so this, we're going to simplify it out. It's going to come to be a quadratic in h prime. So I'm just going to write it out here. So 150 millimeters times h prime all squared minus 7,853.6 millimeters squared times h prime plus 3.141 times 10 to the 6 millimeters cubed equals 0. And clearly the units for h prime is millimeters. And so we can run that through our quadratic formula, and we're able to solve for the positive root, and we get a solution. Solve for h prime, and we get a value of 120.9 millimeters, which is the value h prime, or depth, of our neutral axis. I'm just going to give myself a little bit more space here. And what we need to do now is determine the moment of inertia. So let's get the label in here. Now I'm just going to move that over just to give myself a little bit more room. We'll start working under it. Move it up to the top, give us a little bit of space. Of course, we're using the parallel axis theorem, and so I'll just write that in here, get my pen. So I is equal to the sum of, and that's the moment of inertia about its own component and centroid, plus its area multiplied by d at I squared. D at I, of course, is the distance from the composite neutral axis to the component neutral axis. And so we have two components. We have the transformed concrete, if you will, or transformed steel represented by material, concrete material, and then the concrete in compression at the top. So let's do that. We'll start with the one at the top. And so the first one, of course, we have, it's a rectangle, so bh cubed over 12. And so we have 300 millimeters is the width. Its height is h prime, which we found to be 120.9 millimeters. So that's cubed divided by 12. And then its area is, again, that 300 millimeters times 120.9 millimeters multiplied by the d prime. So if we look at our diagram, we can see the d prime is the distance between the neutral axis and the height, or half the height up, or half of h prime. So we'll put that in here. And so that is h prime over 2. So I'll just substitute right in for h prime, which is, again, the 120.9 millimeters divided by 2. And then we have to add in the value for the transformed concrete. Now, it's typical practice just because the original area, we have an N of 8, and so we typically ignore the original area. It just makes it a little bit tidier. It's a reasonable number given the nature of the work that we're doing. So we're going to ignore that first component, the BH cubed over 12 of the rectangle, if you will. Now, of course, it's not a rectangle anymore. And so we have our area, and our area is represented by 7,853.6 millimeters squared. And that's multiplied by d at I squared. And so the d at I squared in this case is going to be the depth to that, which is 400 millimeters less h prime. So 400 millimeters minus 120.9 millimeters, and that is squared. And I'm just looking, we didn't put in the squared value over here, so we better do that. Go back and put that in, otherwise we're going to get the wrong answer. And we come up with a value of 788.52 times 10 to the 6 millimeters to the 4th. So with that, we have everything we need to start thinking about calculating stresses. So if we want to get our maximum compressive stresses, they're going to happen at the top of the beam or the top of the concrete section. The tensile stresses, of course, will be in the steel at the depth 0.4 or 400 millimeters. We'll start with our stress in the concrete, our maximum stress in the concrete at the top of the beam. So let me get some labels in here. So our stress in the concrete is equal to negative my over I, which is equal to negative. Now our moment was given in the problem is 60 kilonewton meters. So we'll put that in here, and of course that is 60 times 10 to the 6 Newton millimeters. Keep our units compatible. And the y, in this case, is the distance from the neutral axis to the top fiber, which is equal to our h prime, which you recall is 120.9 millimeters. And then we divide that through by our moment of inertia, which we just calculated. It's 788.52 times 10 to the 6 millimeters to the 4th. And we come up with an answer of negative 9.20 megapascals. Of course, the negative implies that it is in compression. We'll put a C for compression, which is what we expected. Otherwise, we would have been discounting that concrete. So everything's working out so far. Now we need to do is to calculate the stress in the steel, but with a prime on it. So in our transformed section still, so again, negative my over I. Our moment doesn't change, of course. It's 60 times 10 to the 6 Newton millimeters. Now, our distance in this case is that depth, 400 millimeters less h prime, which is the distance that it exists from the neutral axis. Now it is going down, so it's going to be negative. So let me just, a little bit more space here, negative 400 millimeters minus 120.9 millimeters. And the I has not changed. We're still using the I of our transform section. So 7.88.52 times 10 to the 6 millimeters to the 4th. And so our sigma S prime comes out to be 21.24 megapascals positive. So that will be tension, which is as we expected. That's why we put the steel there in the first place. But in order to figure out what the actual stress in the steel component itself is, we're going to have to untransform that, if you will. And so the stress in the steel is equal to our factor N multiplied by our stress in the steel prime. And so that's just 8.0 multiplied by 21.24 megapascals, and we get a value of 169.91 megapascals, and still, of course, in tension. So just to wrap that up, I'm going to go pick up the diagram from the example and stick it in here, and it will all make sense, hopefully. And so there you see the diagram. It's showing the stress distribution. We have linear from the neutral axis, 0 at the neutral axis, up to a maximum positive in compression in the concrete, shown at 9.2 megapascals. Nothing in the concrete below the neutral axis. Remember, it's in tension. We're assuming it's cracked and broken and not contributing to the capacity of the section. And then we get to the tensile stresses in the steel, shown here, rounded off, is 170 megapascals. So there we go. We can see the entirety of the problem laid out in front of us. It's a fairly easy process. Transform the section, get the moment of inertia of the transformed section, figure out what the stresses are, untransform the stresses for the original material where that applies. And hopefully that was valuable. You got something out of it. Fairly straightforward problem. And now you're empowered to do similar problems. So we'll see you on the next one.